Welcome to lesson number 7, the geometry of linear function graphs. In last lesson, we explored different forms of representations, one of which was the graphical representation. Well, this lesson will analyze even further the properties of a graph of a linear function. In this lesson, we have 3 objectives. 1, we will discover the standard form of a linear function. 2, we will graph a variety of linear functions. And 3, we will try to deduce some geometric properties of linear graphs. Looking back at the last 2 lessons, let's take 3 of the equations that we encountered and used. In the next visual, you'll see them. Y equals negative 18x plus 250. The second is y equals 25x plus 45. And the third, y equals 2x minus 1. What we want to do today, among other things, is generalize. That means try to find a general form of which these 3 are special cases. In other words, we're trying to use inductive logic to go from the particular to the general, from the specific to the universal. What we can do is notice just from these 3 equations that we have a form, as you see in the next visual, y equals some quantity, which I'm calling box, times x plus another quantity, which I'm calling triangle. Those are just placeholders for some constants. So the triangle and the square are constants. What we mean by constant is a real number. Given a specific line, it is a fixed number and they don't change. Well, how do the 3 examples that we just revisited fit in this general form, which we call the standard form? In the first case, as you see in the next visual, the box is negative 18, the triangle is 250. In the second, the box is 25, the triangle 45. And in the third, the box is 2 and the triangle is negative 1. In fact, we have better names for box and triangle. We've been calling them A and B. So, we can conclude that the standard form for any linear function is, as you can see, y equals ax plus b, where a and b are the constants and x and y are the variables. That is a linear function. And in the next visual, I wrote it differently. F of x equals ax plus b, because I want to stress the fact as much as possible and as often as possible that the y is equivalent to f of x. So whether we write y equals ax plus b or f of x equals ax plus b, they are equivalent. When we use the technology, we'll use a y, but in the books, you'll have f of x. In your school book, in your algebra textbook that you use in your school, you might find that the general form for a linear function that gives lines as graphs is mx plus b. So the m would be our a, and the b is our b. So the b is the same, but the m would differ. The reason I prefer a over m, and it's a choice, it's a personal choice, but I think it makes sense, is that we're going to learn over time and over the next several lessons that this linear function doesn't exist all alone, independently of other functions, but rather it is a member of a larger class of functions called polynomial functions. And if you forget that word, don't worry about it. We'll come back to it. So it is the first member of a whole class. And all the other functions in that class always use a's, b's, c's, d's as the coefficients or the constants. So we're going to start with the simplest in the polynomial family and call it ax plus b. In our graphical exploration, we wish to examine more carefully the impact, the influence of a on the function and b on the function. And how are we going to do that? Well, the way we have to do that is draw a lot of functions, graph a lot of them, and let a vary while we keep b constant, and then let b vary while we keep a constant. And we're going to deduce, this time deductive logic. From many examples, we're going to conclude on some properties that we don't know right now. Let us begin by exploring the importance or the meaning of a in that equation. Let's see how varying a will affect the shape of the graph. To do so, we're going to keep b constant, and more specifically, we'll let b equal 0. So b won't even be in the picture. We'll just look at equations of the form y equals ax. So let's go to our graphing calculator, our computer technology, and let it help us find these properties. Here we have our y equals menu. We can input as many as 8 functions at least, even though there are 2 more that are hidden. Let's start with some simple a values. Let's have a be 1/2, which is also 0.5. So that's 0.5x. The second one, 2x. And the third one, 5x. These are 3 simple functions where a value is the number multiplying x and the b is not there. It's not really absent, it's just equal to 0, so we don't write it down. Let's now graph it. The window that we can use when we don't want to bother with it, we can always go to Zoom and pick the standard, which is number 6. And that's the standard window we've seen several times. So as we pick that standard window, there's the first, there's the second, and there's the third function. Well, we notice several things. The first thing we notice is that the 1/2x slope is not as steep. That's one I might ski on. This slope is 2x, and this slope is 5x. Well, we kind of get the idea from these 3 functions that as a gets larger, the function or line rises much quicker. Well, let's see if our intuition is correct. Here we have a 1/2 and here we have 2. To test our conjecture, let's see if we can fit a line right through here. A line whose slope would be between 0.5 and 2. Well, what's a nice choice? Something between 0.5 and 2 might be number 1. So let's go back to y and add 1x. Well, I just put the 1 for emphasis. We don't really need the 1. We could have put x. And now let's see where that lies. We go back to graphing them again. There's 1/2x, there's 2x, there's 5x, and there is 1x. So our conjecture or our guess that the line rises faster as the number increases was correct. Now here we have 3 positive slopes. A is positive, greater than 0. Let's try 2 negative slopes. Let's go back to y and add 2 more functions. Let's take negative 2x and let's take negative 5x. Well, where do you suppose they might come in? I'm sure you've guessed already. So to confirm what you're thinking, let's graph. We have the first 4 that are positive, that live in quadrants 1 and 3, and here's negative 2, and here's negative 5. So indeed, our negative 2 comes down, and our negative 5 goes down even faster. This time it's an inverse relationship. Over here, 5 was larger, 2 was smaller. Over here, negative 5 is smaller than negative 2. We've got to keep that in mind and remember where those numbers appear on the horizontal axis. Now I'd like to fit something in through here. What could that be? Here's the horizontal axis. This is negative 2. Perhaps something between 0 and negative 2 might fit, something like negative 1 or negative 2/3. Let's try. Go back, and one last one. Let's put in negative 1x and see if that does the job. So one last time, we see them all. And here comes our negative, negative 2, negative 5, and negative 1. So indeed, we have our negative slopes that go here, our positive slopes that go there. Let's use correct terminology. There are two ways of saying it, or maybe more. But when we talk about the graph, which is a line, we can say that it moves upward, or that it rises, meaning that as x increases, y also increases. But another way of saying it instead of rises is to say increases. And when we say increases, we're really referring to the y value. So we say f of x increases. So at this point, we're ready to recap a little bit of what we just saw, or conclude. As you'll see in the next visual, when y equals ax, if a is positive, the graph rises. If a is negative, the graph falls. And notice I put those in quote marks and quotation marks. More formally, or more mathematically, we'll say that when f of x equals ax, the very simple linear term, there are two possibilities. A greater than 0 means the function increases. A less than 0 means the function decreases. Now those two visuals are equivalent. They're just different ways of writing them. And what I'd like to point out to you are the two notations that I have side by side over and over again, because I want you to start writing things more mathematically. And that is, when I say a positive, another way of saying that with symbols is a greater than 0. When I say a negative, that's a less than 0. So two same ways of putting it. And then the other similarity or synonymous expressions are either y or f of x. So whenever possible, I want to emphasize that by putting them one after the other. What about when a is 0? We saw positive slopes, the functions increased. The line rose. We saw negative slopes, the function decreased, or the line fell. What about 0 slopes? We haven't tried that. A equals 0. What would that look like? Y equals 0 times x. That leaves us with 0. So let's plot y equals 0 and see what happens. Let's erase the other ones because we have about 7 or 8 functions and it's like a nice big star. But let's just graph our new line y equals 0 and see what happens. So let's go back to our graphing calculator and input y equals 0. Here is my y menu. I'm going to clear very quickly these functions and go back to y1, it could be any one, and do 0x, which really is 0. And let's graph it. Well, I don't think you saw anything, or maybe you did, but there's no graph up there. What do you suppose happened? Well, we saw that lines that have positive a's rise. Lines that have negative a's go downward. Well, what do you suppose this is? This horizontal line, as we saw way back in one of the first lessons, is the horizontal axis. That's the axis of input values. That means that x varies here. -10, -9, -8, 0, 1, 2, 3. But what is the y coordinate of every single point on this line? Well, y is 0. There's no y is up here positive, y down here is negative, but on the line y is 0. So it's not surprising that this line, the horizontal axis, is y equals 0. So when we just graphed y equals 0, the line went right on top of here and we couldn't see it, but it really was there. So if we can remember and not forget, when a equals 0, we have the equation y equals 0x in this case, and therefore y is 0, and that's the equation of the horizontal axis. That also is something that we can't insist enough on, because we always forget that the horizontal axis is called y equals 0, and the vertical axis is called x equals 0, because on the vertical axis, every point has an x coordinate that's 0. Well, now it's time to go and shift to the b value. Let's keep a constant because we explored all possible values of a positive, a negative, and a 0. That's about all a could be. Let's go to B and keep A constant. A simple value for A to keep it constant would be 1. So the line will look like 1x plus B, and we let B vary. B is going to be positive, B is going to be negative. We're going to try all sorts of values of B, just like we did with A. Well, let's go to our graphing calculator again. So we've decided to use A equals 1, so that's 1x or x. We can just drop the 1, plus 7. The next one will keep A again equal to 1, so that's 1x or x plus 2. And the third function we'll do is 1x minus 5. Now minus 5 is like plus negative 5. So we have a positive b, another positive b but smaller, and a negative b. Let's graph these functions. There's my x plus 7, x plus 2, and x minus 5. Well, perhaps we are getting some idea of what b is, but maybe not. So let's trace. And the spider is here right now, emphasizing that for this line, which was x plus 7, this point is 0, 7. Well, that makes sense. When x is 0, y is 0 plus 7, or 7. Let's trace the next function. And this point, we read the coordinates on the bottom. X is 0, y is 2. Well, this line was x plus 2. So when x is 0, we're left with 2. Y equals 0 plus 2, or 2. And if I trace the last one, this was the line y equals x minus 5. At this point, x equals 0, y equals negative 5. So there's a correspondence between the b value and these specific points. That's the point 0, 7. This is the point 0, 2, and this is the point 0, negative 5. Well, if it's starting to become clear, let's see if, before we state it formally, let's see if we can fit a line through here somewhere. Okay, this was 2x, this was x plus 2, this is x minus 5. So what line might fit in here? Well, let's take a b value between 2 and negative 5. 2 is in this function, negative 5 is here, so what value would you like to pick? Well, let's pick x minus 2, for example. Minus 2 is definitely between 2 and negative 5. It's less than 2 and greater than negative 5. So let's graph and look well, observe the fourth function drawn and see if it does exactly what we want it to do. There's x plus 5, x plus 2, x minus 7, and there you go. It's exactly where we wanted it to be, between 2 and negative 5. So I think by now we have an idea of what the b value represents. Just to make sure, let's try to graph one more line that's going to cross the y-axis down here. Well, this was negative 7, or was this negative 5? Negative 5. Let's go back and find something down here. Let's pick, for example, a negative 8. So let's add one more. This is really to emphasize. I think we've already got x minus 8. And take a look at that fifth line graphed. Plus 7 plus 2 minus 5 minus 2. And there's our minus 8. Let's trace that last one. And indeed, that point is 0, negative 8. So we are ready to conclude another result, that b is the y value of that special point where the line crosses the y-axis. That point is called the y-intercept. So 0, comma b, as you see on the visual, is going to be called the y-intercept. 0 is always the x, but b varies with the lines. b could be above, b could be below, b could be at 0. Well, I think there's something else we can conclude from these parallel lines. Let's go back and look at our view screen. We have parallel lines here. We've talked about these intercepts, so we now understand what they are. We saw that these lines all have an A that is similar. The A, if I look back here, is 1, 1, 1, 1, and 1. We don't see the 1, but it's the coefficient that multiplies x. And you'll never see 1x in a textbook. You'll see x because 1x is x. So maybe there's a correlation between these a values being the same and these lines being parallel. Well, let's check that conjecture and go back and do something called insert. If we insert a new slope instead of 1, let's insert 2. Or in the next one, we would insert 2 again. Insert 2. The next one, insert 2. The next one, insert 2. And the last one, we would insert 2. Let's see if the lines are still parallel, but having a greater slope. They rise even better than before, even faster, and they're still parallel. What has changed and what has remained the same? If we trace, we see that the intercepts are all as before because the b's haven't changed. But what remains the same is that they are parallel. Well, we are ready to make another conclusion, that when two lines are parallel, they have the same slope. Or, reciprocally, if they have the same slopes, they are parallel. That's an equivalence. Written in another form, y equals a1x plus b1, as you see in your visual. y2 equals a2x plus b2. a1 equals a2 if and only if L1 is parallel to L2. Now that's a very symbolic form of notation. But we are in mathematics, more specifically we are in algebra, and that's the type of symbolism we have to start to get used to. Now if you're not going to remember it all, that's fine. You could write out parallel. You don't have to use those two double bars, but it's a very logical symbol. Also, we had that double arrow that you saw in the visual. That means if and only if. That means that the left side is true if the right side is true, but the right side is true if the left side is true. So it's an equivalence, and we say if and only if in English, and we use the double arrow in symbolic language, in algebra. That brings up another question. We now know when two lines are parallel, the slopes are equal, but what about two lines that are perpendicular? Well, that's another exploration that we need to do. So let's erase the lines we have, pick one line, 2x plus 1, for example, a very simple line, and explore by trial and error. You can do that too at home, and find a line that would be perpendicular. So let's go back to our graphing calculator to help us out. Let's type in 2x plus 1, a very simple function, and graph it. And the idea here is to find a line that is perpendicular to it. Well, we have no clue what that slope will be, but we have one idea, and that is that it comes down. The line will fall. So we learned earlier that that slope is negative. So let's try a negative slope and see if it's perpendicular. Well, your guess is as good as mine, so let's try negative 1x or negative x and graph that and see what happens. Well, that looks pretty good, but we're not really sure because this is not a perfect screen. These pixels aren't perfect, and there's another problem. These units here are longer than these units, so we might have an optical illusion here because they're not the same length. Well, our graphing calculator has a very interesting feature that we could go to zoom square, which we haven't seen before, under our zoom menu, and square just means that the x and the y units are the same. So let's pick 5 and now graph them again. And now we see that they're not really perpendicular, but you do see that this distance and this distance, the unit values are the same. So this was a bit too steep. We want something to come more like this, at a right angle. So let's erase that one and try, let's erase that, so I have to clear it. And let's try, of course, magically, negative 1/2. Well, negative 1/2 is negative 0.5x. Now, of course, this is where the teacher's knowledge helps a little bit. There's 2x and there's negative 1/2. Now, that looks pretty good. Now, of course, I don't expect you to have found that right away. It would have taken a lot of trial and error, but here we do look like we have a right angle. Now, what is the magical relationship between 2 and negative 1/2? Well, if I look at 2 and negative 1/2 and multiply the two, it gives negative 1. Another way of putting it is that 2 and negative 1/2 are negative reciprocals of each other, meaning 1/2 is the reciprocal of 2, but negative 1/2 is the negative reciprocal of 2. Well, let's test that one more time and draw two other lines, like 3 and negative 1/3, and see if we still have perpendicularity. Then we're done. So clear, clear. Let's do 3x, and we can make b equals 0, would be easier. Negative 3, no, sorry. We want to do negative 1/3 x, and that looks a little complicated, but there's your negative 1/3, and let's see if they're perpendicular. Indeed they are. So we are ready to recap and say that two lines are perpendicular, as you see on that visual, if and only if their slopes are negative reciprocals of each other. Well, how do we put that? Well, if one line is written y equals a1x plus b1, and the other y equals a2x plus b2, the product of a1 times a2 has to equal negative 1 if and only if those lines are perpendicular. Our final remarks for the class, I'd like to recap right now. As you can see on the next visual, I'd like you to remember that a function is linear if and only if the algebraic expression is ax plus b and the geometric representation is a line. Those are the two meanings of linear. Algebraic is the equation, geometric is the line. In terms of a, if a is positive, the line rises. The function increases. If a is negative, the line falls. The function decreases. If a is 0, the line is horizontal. It doesn't change. It's constant. As for b, we learned that if b is positive, the line crosses the y-axis above 0. If b is negative, the line crosses the y-axis below 0. And if b is 0, the line crosses the y-axis at the origin. What are the coordinates of the origin? 0, 0. Not only x is 0, but y is 0 too, because it's the intersection of both axes. So if you can remember those two meanings, the meaning of a and the meaning of b, you've learned a lot. I'm going to leave you with a few functions to look at, and I'd like you to test your knowledge from this class. If you can look at this first function and say the slope is positive, so the function will rise. The b is a negative number, so the function crosses the y-axis below the origin. That's having learned a lot. Here, if you look at this function, you see that the slope is negative. The function falls. The line goes downward. The b is 0, so it crosses the axes at the origin. Here, we have two same slopes. The lines are parallel. These are negative reciprocals, but that doesn't mean anything because they're the b values. Over here, our slopes are negative reciprocals of each other, so they are perpendicular. One b is 0, the other b is 1. That means that they have y-intercepts that are different. And finally, I'd like to leave you with a thought. Don't forget that if a is 0, the line does not rise, it does not fall, it stays constant. That means the line is horizontal. So if we have a line 0x plus 3, it's horizontal going through 3. If it's 0x minus 5, it's horizontal going through minus 5. We always forget the 0. And finally, if b is 0, you know what that means? It crosses the vertical axis, the output axis, at the origin. Those are the two thoughts I'd like to leave you with. Practice some more. Practice makes perfect. And by next lesson, I'd like you to know, like that, the meaning of A and the meaning of B and all the different values they can take.